G'day comrade subscribers. I thought we'd stick with the VIC-20 whilst I've got it out. So one of the things with the VIC that I've always been kind of fascinated or obsessed with is reducing their waste heat. So I figure with old computers, the less heat they generate, the less waste heat they generate, the longer they're going to survive, perhaps. So one way of doing that is by reducing their power consumption. So the VIC-20, certainly the original two-prong 9-volt ones are really good for being able to reduce their heat because there's lots of opportunities. So it's powered by 9 volts AC. So that means that we need to come into a rectifier down here, which I've got covered with a ceramic heatsink. Normally there's another big heatsink in there, but you can't see half of it. Anyway, so it comes down to a rectifier there, then it goes through a regulator here, a linear regulator. So we've got heat being generated here, we've got heat being generated here, and then obviously we've got the CPU, so that's going to generate heat. We've got these ROMs here. I think we've got basic and we've got the kernel. They generate heat. Character ROM here, not so much, but it does generate some heat. Obviously the VIC chip itself, so this is a 6561, that's a good source of heat. The VIAs, versatile interface adapters, 6522, one for the keyboard interface and one for the expansion interface. They also generate heat, even though, for example, one of them's not doing anything most of the time. We've got the RAM down here. This generates heat. So what can we do? Well, as you can see in this one here, well, one thing we can do is we can, for example, bypass the rectifier by putting 9 volts DC directly into the regulator. The rectifier is not being used, it's not generating heat, we're reducing power draw already. We can replace the original linear regulator, LM323, with, for example, a PSU5 from ezsbc.com, which is what I've got here. So a modern switching power supply, that reduces heat massively as well. So we've got we're already reducing our power draw by doing those two things here. Obviously you don't need to bypass the rectifier. One of the benefits of keeping it is if you're putting in 9 volts DC is that it doesn't matter about the polarity. The rectifier is going to sort it out. Replacing the ROMs is another good way to reduce power and reduce heat. These are, I think they're 23 series. So replacing them with, say, modern 27C EEPROMs reduces the heat quite a lot on those as well. Character ROM, I guess, yeah, you could also save a bit of heat there. I'm going to come back to the CPU, the whole point of this video. And the VIAs, these can be swapped out for a 65C02 modern versions. They're still manufactured, and they go from like 40-50 degrees to room temperature. So that's a very easy saving there as well. We've already looked at the RAM replacement in my last video, so we'll see how that goes. Not much we can do about the VIC chip at the moment, although I think maybe someone has designed a drop-in replacement. Not too sure. Best you can do at the moment is put on a heatsink, which causes its own arguments. People say, oh, you're wasting your time with a heatsink. If it required a heatsink, they would have put one on in the first place. It's like, well, when these machines were being produced, they weren't expected to run for 50 years, and they were being produced for as cheap as possible. So if you're going to put on a 5-cent heatsink, on a million machines, that's $50,000. That extra. So they're not going to put on a heatsink unless they absolutely have to. And back then, if the VIC failed, you just take it back to Commodore and get a brand new VIC. They don't make these anymore. So anything I can do to reduce the heat consumption, I feel kind of would extend its life. That's my view, but anyway. These buffers down here, or the transceivers, 74LS245s, you can swap these out for, I think, 74HCT245s. These also generate a lot of heat, waste power, so you can swap these out. I think you can save a bit of power there. And the 6502, they still make, you can get a 65C02 from WDC, Western Design Center, but it's not drop-in replacement, drop-in compatible. You need to design a daughter board to be able to swap it out, and that's the whole purpose of this video. It's something I've been wanting to do for a while. The Byte Addict, they've already designed one. They've made the files available for download, so you can actually just download it and make your own board. I'm hoping to maybe go a slightly different route, see how we go. But yeah, so that's the purpose of this video, is to come up with something so that we can replace the 6502 with something that's lower power and, you know, reduce the heat consumption. So let's see how we go. So we've already done the schematic. We're at part 6 of the video series now, so we don't need to start from scratch every time. But you can see here I've made a 6502 symbol, and I've made a 65C02S symbol. So that's pretty standard, you know. You just we'll go through quickly. Symbol editor, blah 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 blah, and where are we? So here's the symbols I've made. So it's just basically draw a rectangle and then add in the pins. But you notice the way I've done it is I've done it as per the pin name, not the pin number. It doesn't matter what order the pin numbers are in. That'll get sorted out on the footprint side. But I've done it like this way just to make it simpler when I actually do the schematic, which we'll see in a minute. So this is the 6502, and then I just simply duplicated that, or duplicate as the Finns would say. I just duplicated that to the 65C02 and then modified it. So you can see here, for example, we've got these unconnected pins. The naming of these clock pins is a bit, it varies depending on what pinout you look at. I've gone off the VIC-20 schematic, so that's why I've just called them like that. So like I said, just duplicate it, and then I've modified it as per the 65C02S, I should call that S, pinout. So yeah, so that was creating our and then basically this is the design. So as I said, like you can see here, the way I've done the address pins. So if we just go through and delete these, well, basically you can, once you've done, for example, you do your bus here, and then you do your bus connectors. So you do the first bus connector, then you press F1, and it will duplicate them all the way down. Same here. Can I do that? No, because I need to do that. I'll delete it anyway. And then same with the wires there, and then same here. So A0, I can label that Y, and then just simply do F1, and it'll go A1, A2. It'll increment automatically. So that's why I've done it like that. Same with the data pins, even though they're around the other way. Yeah. So let me just actually, because I've gone and deleted that now. I'll just Control Z, go back. There we go. So basically, so what we're doing is the daughter board. So we've got the 6502 socket, so that's going to plug into the VIC-20 motherboard, and then this is going to be the new 65C02S from from WDC, Western Design Center. As you see, it's got a couple of extra pins. So we've got some notes down here that we've taken from the we've got the website. So this is their website here. So replacement notes for obsolete versions with their new ones. So you can see, actually, unfortunately, it doesn't seem you can do a universal conversion, because the Apple I, Apple II do slightly different things. And it looks like there's so many different versions of the 6502 out there. Yeah. Anyway, so I've gone through this and basically made a note of the requirements. So in summary, so this is the new chip that we're putting in. Is mostly pin compatible, making the following modifications, which is what we've done on our schematic here. So for example, on pin 1, on the, I think it was ground VDD on the original 6502, but on the modern one, 65C02S, pin 1 is the vector pull pin. So the vector pull, so there I've got it disconnected. So if we were, say, if that was the only difference, then what you could do is you could plug this new chip into the VIC, and then just leave pin 1 kind of, you pull pin 1 up so it's not actually in the socket. Anyway, what else do we have to do? So the ready pin should be pulled up. So we connect, so that here we've got ready pin. So here I've used a label, and then we've got the ready pin over here. But it needs to be pulled up because apparently we've got internal pull-ups on the old chips. On the new chip, it doesn't have an internal pull-up. So I've got to pull up to 5 volts, 3.3K, which is what it recommends on its website. But then it's still connected through to the ready pin over there. The memory lock should be disconnected, so it's a not connected pin on the original. So I've got MLB there, not connected. Bus enable should be tied to ground, because I think it's probably active low or something, is it? I don't know. Oh, hang on. Bus enable should be tied to ground. Why have I got it pulled to 5 volts? I made a mistake. Bus enable should be tied directly to VDD. Hang on, VDD is... Oh no, VDD is 5 volts. VSS is ground, that's right. So that's correct. So it should be tied to... Oh, okay, let's... Ooh, good thing I double checked this. Should be tied to plus 5 volts. There we go. Yeah, because if it was active low, then I would have marked it as active low. Okay. So that's, I think, basically the main things. The other main problem is that the data bus needs to go through a transceiver or a buffer. So a 7.4 HCT245. Yeah, so they didn't have a 7.4 HCT245 in the if you do a search 7.4 HCT, they don't actually have a 245, they've got a 244, but you know they've got an LS, so 7.4 LS 245. So I've just put that in, and then I've just changed the value from LS to HCT. It doesn't matter. It's just the label. It's the same pinout. And then connected up. So the direction based on the read write signal. So whether we're reading data or we're writing data. Ground for chip enable, active low. And then we've got some decoupling capacitors here just to give some local power reservoir. And and then I've just named the bus. So as you can see here, so we've got A 0 to 15, D 0 to 7, and Phi, the clocks 0 to 2. So that's why I've named the clocks like this, Phi 0, Phi 1, Phi 2, just so I can do that bracket rather than naming them individually. And that's basically the schematic done. Like I said, everything else is connected through. Yeah. So when we assign footprints, so this is not how I'm going to do it. I'm just showing this is how I traditionally would have done it, using dip and through hole parts. But that's what Byte Addict have done. So it's like, well, there's no point in me reproducing what they've already done. So you can see here, this is what Byte Addict did 5 years ago. So I'm pretty late to the party. So you can see this is a I think it's a VIC-20 CR, a cost-reduced VIC-20. So you can see it's got the 9 volts and the 5 volts in, which I don't like. I don't like those VICs. So he's done 2 versions. He's got this version here, and as you saw in our VIC-20, the 6502 was actually horizontal. So he's actually done 2 versions for us. But yeah, so the GitHub's here, so we can download. So we've got the long adapter, short adapter. So we can use that, but like I said, I want to add value, so I want to try something a little different. So if we just go now to update PCB, okay, close, then we've got all our parts there. So this is our socket, so this is what's going to be, alright, so it's oriented like that. So let's just get these things out of the way. We're not going to do too much with this because I want to actually use surface mount. Now traditionally what I would do for a daughter board is like this. So just to minimize, and you can see most of the pins are direct connection, right? The address pins and things like that. It's just these data pins, the data bus here, D3 and this one here, has to go via this 245, this massive thing over here. So what you traditionally do, I guess, is something like this, and then we've got our pull-up resistor, so stick that there, and then we've got our two decoupling caps, one for the bus transceiver. So let's just stick it there, and then I guess you can just stick this one here, whatever. Come on, there we go, whatever. Okay, so if you do a quick view, so it would look something like that. You can see it's a bit of a mess actually. So we'll fix that. Well, let's just fix that quickly. So this original one here, the 6502 socket, so if we double click on that, 3D models, so you can see at the moment it's a chip, but it's actually just going to be a row of pins, because this one's actually to plug in. So let's just get rid of the 3D model, and that's kind of more accurate. It would be good if we have a 3D model with just pins, but that's that's enough. Now if we have a quick look, and that's more basically what it's going to be. So you can see here I'm using a socket. I could replace that and just do that as a chip, but normally we just use a socket, so we can replace it easy. And that's basically it. So it's very similar to what the byte ASIC have already done. Maybe I could, I don't know, change it a little bit. So let's just quickly do some routing, edge cuts. So let's actually draw up a board. So say that'll be our board there. Let's do a ground plane. So the bottom copper, and just the same size as the board, and it's going to be ground plane there, and just do the same size as the board. Now normally also I'd fill at the corners so they're nice and round, but anyway. And then we go to good old Freerouting, and let's see what happens. Start. So, okay, so two connections not found. So if we have a look at that, okay, so you can see ground. That's not a problem because we've got that ground plane that we've designed. But let's just fill that in. Okay, so what's the actual problem? Aha, D7. D7 couldn't be routed. So you can see the way it is. So D7's got to go from the VIC-20 to the bus transceiver, and then there'll be a net D7. Here it is, and then that's got to come back out again and go to our chip. So that one's all right, but it's the original D7 hasn't routed. So and there's one over here. This one here, I would say, looks like, yeah. So you can see here the ground is isolated. So we've filled in the ground here, but it's not actually connected to the rest of the ground plane. We can usually probably fix that. So we could actually do something sneaky. We could try something like this, and we could actually just draw a trace through like that. Yep, that's all good. And that technically, and then if we fill all zones again, well, still complaining, but whatever. Okay, it's complaining about D0. Oh, no, okay, it's actually D0. But that ground plane there is actually isolated anyway, so it is complaining about... Okay, so D0... yeah, it's this one here. So that one they couldn't route either. So how do we solve this? Well, if you make the board larger, that'll fix it. Usually, because it can, it's got more space to route them. So if we just unfill all zones, okay, which one is that one? Well, that's the ground plane. So let's just make the board a bit bigger. So if we have a look now, 3D viewer, got this nice big board. So Right, and then if we just, let's get rid of all the tracks we've got at the moment. Beep beep. Okay, let's run free routing again. It's, what is it here, Sunday? Alright, let's go. Line connection not found this time. So which one is it? It's the same one. D5 this time. So there are things like free routing does some weird things. Well, I don't know, could probably fix it, but you know, for example, we've got all these connections here on the bottom. It's like, well, that's where the ground plane is. Why don't we just stick them all on top? So we can actually, so what I've started doing is I've started manually routing some of these things myself. So let's just select those tracks, for example, and then go to properties, and we can actually change them. So we can switch them up to here. Actually, before we do that, let's just fill in. Let's fill in all zones. All right, so you can see how the ground plane hasn't gone through there. So let's just change these tracks to the top copper layer, like so. And if we fill in again, like that, see, like that. So yeah, but anyway, so what can we do? So we could probably, what we need to do is just unfill all zones, and let's delete everything. Delete all the tracks. And let's just move this up a bit more, something like that. Okay. Now, maybe even moving that a little bit back. Anyway, so this is just showing some problems. The routing, let's see how we go. 5 connections. Anyway, it's getting worse. Yeah, maybe we need to move this down to this side, for example. That might be better. But anyway, I don't want to do it like this. So let's just delete all that. Let's go back to our schematic and try again. So like I said, so Byte Addict have done quite a nice, they've got quite a nice, I think is it README, where is, oh no, here we go, documentation. He's done quite a nice PDF actually. Once it loads. Very, very nice. So you can see here, this is the side-by-side one, and I think, does he show? So that's the side-by-side one for the cost-reduced one. And I don't know if he shows the, oh, here we go. So this is the one. So you can see he's got the 6502, and yeah, so he's actually got it on the bottom side, which is what I was just talking about there, the transceiver. So that's the board that we're going to be looking at. But anyway, like I said, what's the point? You know, Byte Addict's already done an excellent job, so what's the point of this? Well, the point of this is to learn how to do it. But yeah, so let's instead of doing through hole, let's try surface mount. Okay, so what we can do, so we can do surface mount for the capacitors, we can do surface mount for the resistor, and we can do surface mount for the transceiver. So let's have a look. So I've already had a look. So I've got them ready to order. So I think I had a look at, here we go. So 3.3K, okay, and it's 0402. So that's what we need to assign our footprint. So it's 0402, and I think it was the same for the capacitor as well, 0402. Now for the transceiver, we've got some surface mounts here as well. There we go. All right, so so SOIC TSSOP, which is the smallest? I'm not sure off the top of my head. Let's try that one. So I think I do have a data sheet open, but let's have a look. That's slightly cheaper as well. Let's have a look at this one. Okay, data sheet. Okay. Now, what's the size of it? It was SSOP 20. Was it TSSOP? That's not the one we're looking at. Which one was it? PW. TSSOP. Okay. Okay, body width 4.4. Okay, so let's go back here. Let's assign footprints now. So let's replace the capacitors. Capacitor, surface mount. What did I say? They were 0402. Hand solder. Definitely hand solder. Okay, same for the resistor. So have a look at resistors. Surface mount. I should have just left that 0402. Yep, I think that one there should do. Okay, so 6502 socket, that stays the same. That one stays. So this is the one we want to change here. So package, I think package SOP. Do we have package SOP or package SO? That might be the one. Let's do, can we do TSSOP? Okay. Let's go back and have a look. Oh, it's 20, so do we have a 20? Okay. I don't know what the difference, here we go, TSSOP 4.4. So body width 4.4. Do we have physical dimensions? Dynamic. Okay, here we go. So SO20. Is that the one? SSOP. TSSOP. Okay. TSSOP 20, 4.4 by 5, pitch 0.04. What's the pitch? Is that E? Is E the pitch? 0.65. This one here, 0.65. You reckon it's that one? Let's do that. Okay. Alright, so let's try the PCB again. Update. Close. Okay. So let's do this again. So what we want, we've got the socket, so let's just get rid of the 3D model, like so. And then we need to rotate it so it kind of matches what we've got in our mind of where we need to plug it in. Now, let's put that straight on top, if possible. Now, what we can do here is we can try and do something like this. We can stick it in here, like so. And then obviously same with the, let's have a look. So what do we got? So we've got the pull up. Let's just get rid of that. Now the pull up I think was on the ready line, wasn't it? Now let's just smooth that so we can see that on the silk screen. I know I should keep the part numbers, references, but there's only one resistor. So, all right, so there's the ready line. So let's rotate that around. Just trying to minimize the tracks as well. So here we've got ready, connects to ready, connects to ready. So that's right. Okay, ready connected, but we've also, this is also pulling up to 5 volts. So that's correct, which is down there. Okay, now we've got the decoupling. Just to add a little bit extra local power. Let's get rid of that. And we could probably, there's 2 capacitors. All they're doing is decoupling. So I don't think you really need that. I'm just trying to minimize what's on there because they're quite small as well. But I'll put that on the silk screen. Probably let's get rid of those as well. Don't really need them. Okay, so if this is going to be the decoupling for the transceiver, Okay, where's 5 volts? That's the 5 volt power there. We'll just rotate that around. Let's get rid of that. Let's get rid of the we don't need that. We don't need that visible. Maybe we'll keep that. Let's stick it on the silk screen. Okay. So the decoupling cap. Now we're going to have a ground plane, so it doesn't really matter about ground. Ground's going to be all around. Okay. Let's get rid of this. Worry about this later. This is all over, all written over each other, and I'll probably edit the footprint or whatever just to get rid of. Anyway, we'll worry about that later. Let's see if we can actually get this to route. Now let's bring the other decoupling cap down. So this is for the 65C02. So again, let's get rid of that. We don't need that. We'll move this to the silk screen. So it'll be printed on there, and we don't need that reference. It's just extra. It won't even be printed anyway. So this is for the 65. So ideally, you'd want this near the 65C02's power, 5 volt line. Even though it is getting 5 volts from the board, you know, the idea here is that it's got a local reservoir power it can draw on, like so, something like that. So if we have a look at this now, we don't need to draw edge cuts. Let's just have a quick look at the 3D viewer. And what do you reckon? That's basically the size of the chip we're replacing. So that's pretty cool if we can route it. So one thing I've started doing actually is with the 5 volt line, or the power lines in particular, I've been manually routing them. So we've got 5 volts to 5 volts, and then we've got that down to there, like so. Actually, what I should do, if I rotate this around, not like that. It's probably because I've routed. Let's just not route it first. Okay, now let's rotate that around. Yeah, that's what I wanted to do. Okay, bring that down a bit. Rotate that around, stick that there. So now we can route the power like that, and then across. Not so important because that's just a pull up. Should have it in line. Doesn't really matter, but it's just, you want it like that maybe. Sorry, I know, skip ahead if this is boring. There, and then route that over to there. And then we could also route it. We could probably like so. And then what I've been doing is I've been making them a bit thicker. So I think that essentially this one's not so important, but because just a pull up. Maybe let's just, yeah, okay. So now what we can do is I'll just make it a bit thicker. So edit track, and so let's we've only got tracks at the moment, so and these are the only ones we've done. Actually, to do that, what we need to do is we need to go to board setup to do it this way, and go to design rules, predefined sizes. So if we add, say, 0.5 mm track, like so. So now what we can do is we can go, because we've only done those tracks, so that's we don't have to worry about anything. We can change the track width to that, and now the tracks are just a bit thicker. I don't know if it really makes a difference, but all right. So let's, after all of that, let's see if we can actually route it. So to do that, we need to actually draw our board.
You know, we can make it a smaller spot. Let's just make it a little bit bigger, like so, like that, and then we'll do our ground plane again, like so, and like so, like that. So if we have a look on the 3D view, again, oh yeah, again, what I like to do, it's probably not worth doing it now, but it's not what I wanted. It's the edge cuts that I wanted. Is I just wanted to go properties, shape modification. I just like to, like I said, just so we've got nice round corners. Okay, I have looking at 3D viewer. So if we can route it, that's basically what it should look like. So hopefully it's a small little improvement. If we can route it, if we can get it to work. So let's see if Freerouting can do it. Start now. One connection, so yeah, we're still having problems. So ground, okay, ground's not a problem. But you can see here, you know, we've got all of these here, so we can move all of these, because if we can move all of these to the top layer. But what's the problem? What's the problem? It'll be one of these, yeah, it's D2 this time. You can see it's D2's not routed. That's the problem there. So you can also double check as well. So you can go to inspect design rules checker, and it should highlight. We've got 12 errors. I'm not too worried about that. What about the routing? Oh, here we go. Unconnected items. Here we go. So track ground. Okay, looks like we've got might have isolated grounds again. And then here we go. Yeah, D2. So it's just a matter of trying to figure out the best. So, you know, if we're going to stick with this design, all we can really do is move it up and down. Try and get, you know, we could probably maybe move the chip up a little bit, maybe like that. Give it some more room. Let's have a look what that looks like. So we'll give it a little bit more space like that. So let's give that a try. Let's unfill all zones. Let's do global deletions. So actually what I might do is I might just, oh, see, you can lock the tracks as well. Let me just move this. All right, let me just, I'll do some basics and then we'll be back. So we can try this again. So I've drawn in the power again, so slightly thicker, and I've locked it. That's what this little purple outline here is meaning, it's locked, so it won't get deleted if I just delete everything. And then I've just gone through and just connected up the tracks on the top copper layer. Yeah, so I've moved the transceiver down a little bit. See if that's going to give it a bit more room. So let's just try that again. Free routing. Start now. Alright, still having a problem. And this is where other people will be yelling, saying, just route it by hand. So, okay, I'm not that clever. So you see, we're not too worried about the ground. What's this one here? So it's D2. So D2 is the problem now, by the looks of it. So it's just a matter of keep trying. So I could maybe try and rotate this around, see if that'll fix it. Or move it further down here just to see if that giving it extra space will fix it. So where is it? So D, it's this one here, D2. Yeah, so you can see it's surrounded. We've got top copper, and then we've got bottom copper there. So can we route it? Yeah, there's no space there. There's space there, but we need to get across there. That's the problem. So can we go, where was it again? It was D2. So we can go bottom layer to a via. Let's see if we can do this. Let's see if we can do it. Oh no, because we've got this bottom layer going straight through the middle of it. And then if we do it, if we try and do the track, it's going to take it straight at the bottom there. Yeah, that's the problem. We can't. So we need to go top layer, but then again we're surrounded by those. What about if we go? All right, I'm going to have a think about it. So we can either keep trying with free routing, or we might have to route some of this by hand. Just trying to think. All right, let me have a fiddle. So I got rid of all the manual routing I did, especially down here, and that looks to have solved it. We've got everything routed. So let's have a look how the ground goes though. Let's see if we're going to have any isolated grounds. Fill all zones. Looks like, yeah, looks like we might have one here. Yeah, this little pocket here is isolated. So what we can do there is we can put a via in over to here, can't we? See up here, so like for example, if we move, let's move all these, right? Let's do all these, because there's nothing up here. Let's do all these. Oh, yes, Mama. Is that you knocking on the door? Maybe not. So let's just do all these. Okay. I'll be back. All those tracks to the top copper layer. Let's just fill in the ground plane again. Alright, so we still have that isolated there. But you can see we've got the ground plane nicely up there as well now. We could make this a bit bigger. Anyway. Let's see, so this ground plane is isolated, so what we need to do, I guess, is put in a via. Do I stick the via there? Okay, and then let's put a track in, over straight across to here. You can stick it there, but let's just stick it across to here. You know what I mean. And then we'll stick in another via, like that. And that should, as you can see, that should solve that there now as well. I think that should be everything. Let's run design rules checker. Oh, 10 errors, courtyards. Oh, here we go. Clearance violation, clearance 0.2, it's actual 0.136. Is that because I've made, where is that? Oh, that's okay. Complaining about courtyards. I don't care about courtyards. Courtyards overlap. Well, I can delete all that. So, track 5 volts. Oh, that one there. Okay. And that, oh yeah, okay, see, yeah, okay, that was one I manually routed. Yeah, fair enough. So what I could do there is if I, oh, that's locked at the moment, so if I just select, if I can select that track, oh, well, yeah, I'm on the right layer. Footprint, no, I don't want the footprint, I want the track. Anyway, let me just fix that up quickly. Done. So after some fiddling, I managed to get it deleted And I've rerouted it so it's not so close. And everything else is routed. I've moved the edge cut of the board around a bit so it's more central. So we have a look at the 3D viewer like that. Looks okay, doesn't it? Just one more. It's like, why? Okay, so this is the ground. Why do we have? Why don't we just connect directly to ground from there? I don't understand that. So if we go over here, or can we just stick a wire there, or do we have to just, no, what's that one? That one, yeah. Well, oh, okay, I have to do a via, do I? That's not what I meant. So can we just stick a via there? Maybe not. Maybe that's okay. Maybe that's how we're supposed to do it. Okay. Let's put it back how it originally was. Like that. So that's basically it. Done, I think. We'll give it a try. So what do you reckon? I'm just going to tidy up the this here, for example, get rid of those and just tidy it up a little bit and put some more text on it, so, you know, conversion board and stuff like that. But that's the design. Let's see if it works, shall we? We'll send it off and to PCBWAY, and so I'll finish it, but again, we can just use PCBWAY's plugins here, and so this will go straight to their website. They've got another plugin there where you can just generate the Gerber files. There we go. Get 10 for $5 with global direct shipping, another $5. So $10 shipped to Australia. And because we're using the plugin, they'll donate some of the order to KiCad as well, to the KiCad project. Okay, hopefully that was of some interest. Let's see if it works. Bye for now.